Good morning and welcome on the next webinar focusing on the new topic or topics from helpdesk, hot topics from helpdesk. Let me introduce speakers. Myself, my name is Lucas, and my colleague Petra. Hello, Peti.
Hello, everybody.
So, and some small intro to the GoToWebinar. We are using platform GoToWebinar, so everybody is in listening only mode, and you can type in your questions to the questions window, which you can see here, and we will answer the questions during the webinar or after webinar. Just agenda. So I will pass the word to my colleague Petra, and she will go through the agenda and through the whole webinar. Petty, it's yours.
Thank you, Lucas, for the introduction. So I'm going to share my screen and switch off the camera. So I hope you can see the slides. Okay, so this is the agenda of our of today's webinar. As the title says, we are going to focus on 5 interesting questions or topics asked by our users. So I'm not gonna read this topic. But the thought is that I will always present the question, the topic, say something about the theory, and then switch to software and demonstrate it where we can deal with this problem. So let's start it. Let's get started with the first question response. Before we go to the actual topic, the response, I would like to remind you that there are 2 methods how to assess flexure resistance in IDEA StatiCa. The first one is assessing the interaction diagram depicted on the left. And the second method called response NMM. So this is the method we are going to talk about and say something more about this code check. So what is behind this? If we say we are finding response NMM, so it is actually the method where we are looking for the equilibrium state in the cross-section in order to get an idea of real behavior of the section subjected to internal forces. The result of this method is that we have stress-strain distribution with respect to the acting internal forces. The principle consists in gradual load increment of the section by the unbalanced components of non-transferred forces, which are obtained by integrating the stress over the section using the stress-strain diagrams of the particular material. In general, there are 3 types of material: concrete, pre-stressing steel, and reinforcement. This method is based on numerical methods, especially when we need to integrate the stresses or solve nonlinear equilibrium equations. The whole method is based also on iteration process, so we need to satisfy the convergence criteria. Once we satisfy convergence criterion, we can say that we have the results and we have the response of the section. I think it's maybe more or it's better to explain it graphically what's behind this method. So let me switch to this slide and demonstrate it by these pictures or diagrams. So at the beginning, we call it initial state or starting point is that we consider that we have a section which is consist of linear elastic material. So we assume that the behavior is linear elastic. It means that the section is formed by one material, and we do this by the transformed characteristics. At the beginning, we subject this section to permanent load effects, including creep and shrinkage, and if there is prestressing, defined also by the primary forces due to prestress. So we get the solution, some linear strain, and we go to stress strain diagrams of each material and check if the strain is real and where we are in the stress strain diagram. So let's suppose that we have a strain which is on the elastic branch, so we can easily look up for the corresponding stress. In this case, there is presented a bilinear stress strain diagram for concrete. In general, we can have a parabolic or rectangular parabolic stress strain diagram. And also we need to check the strains in each component. So then we deal with reinforcement and pre-stressing steel stress strain diagram. If we find the stress, we can say that we found the response. If the strains are larger, we are on the plastic branch of the stress strain diagram, and some not transferred stresses occur here. We need to integrate them and subject the section to these integrated forces, so they are here, and find the equilibrium together with other components of the loads, such as variable and secondary effects due to prestressing. This is the iteration process. So we need to find the equilibrium. So we need to look for the position of the neutral axis, or we need to find the plane of strain. Once we find it, then we can say that we have the response. So this is the usual procedure, but we can also have the situation that the strains are unreal. In other words, they are out of the stress strain diagram. So in that case, we need to reduce the action loads and go back to the beginning and start with the lower internal forces, subject them to the section, and again calculate the linear response. So I hope this picture helped you to understand it better. And now I would like to switch to IDEA StatiCa RCS, the application for checking the sections, and demonstrate where we can find the response. So we have this reinforced concrete sections. There are only reinforcement, no prestressing. And it is subjected to internal forces. They are input here. So we have some bending moment, and in this case, no normal force, but in general, there could be some value. We go to results and we got the checks, but there is no response. So by default, it is turned off. So we need to go to calculation control and check this on, then go to results, and as a last tab, there is the response. So I will click on it, and I can see what is the response to the internal forces, which are also stated here in this table, current extreme forces. What did we get? We got strain distribution and stress distribution along the height of the cross section. We can see the values for the concrete and for the reinforcing bars. And we can see that the concrete in tension does not act. Instead of that, we have the reinforcement here, and that the concrete is in a plastic branch. This is the basic or default view. We have on this view a ribbon, other options like 3D, so you can look for the distribution of strains and stresses in 3D. Then there is another type of displaying. You can see the resultant forces, so the compression in concrete part and tension in reinforcing bars. And as a last, there is possible to display the diagram, the individual diagram for each material. So here we have a parabolic stress strain diagram for concrete. This is in compression. And if we click on this fiber, we can see the actual strain and stress in this fiber. If I click for example, on this reinforcing bar, I can check what is the values for this compressed reinforcement. So it is in compression, and again, we have stresses and strains. And here, if I click on this, I can check the values for this most tangent group of bars. So we have strain and stresses. So the user can get the imagination how it is in this cross section if it is subjected to these internal forces. So we can get some imagination and we can see the actual response. Okay, so let me switch to second question. The second topic is how is the pre-stressed concrete section assessed in IDEA StatiCa? We are gonna talk about assessing of ultimate resistance of cross-section in bending. So in general, there are these two methods how to check it. First is according to or by interaction diagram, and the second one is the response, which we have discussed before. So now let me talk about the assessing by interaction diagram. So the procedure is as follows. We need to assess the decompression stress, which helps me to convert this pre-stressed section to the non-pre-stressed one. We do this in order to get the non-pre-stressed reinforced concrete section, because then we can continue with the classical theory, ultimate limit strain, once we know the decompression stress. So this is the step which is different from the regular reinforced concrete section, and from this step it is the same, the procedure. So we need to find or assemble equilibrium condition, force equilibrium condition. From this equation we can get the position of neutral axis, and once we know this plane of strain, we can check the reliability condition in moment resistance. So at this bottom part of this slide, I added a picture which is borrowed from the code actually, and this is the general cross-section of general shape, reinforcement, pre-stressing steel, and here you can see the characteristic points of interaction diagram and strain of pre-stressing steel, and also the contribution in pre-stressing steel. Again, I also added a picture of ultimate straight method. So here it is depicted the procedure. Of course, this is borrowed from the materials from the university. So this procedure corresponds to manual calculation. So if we calculate by hand, we usually deal with some simplified stress strain diagrams. It means that we have horizontal plastic branches and simplified distribution of the stress in concrete, but the principle is the same. We need to deal with force equilibrium condition, and then we can check the moment reliability. If moment of resistance is higher than the moment corresponding to external forces. In IDEA StatiCa, there is a small change or difference, let's say, that you will find the effects of pre-stressing, the primary effects of pre-stressing on the left part, in this case, on the left part of the equations. So it means that we add the contribution of the pre-stressing to the side of resistance of the section. So let's go to IDEA StatiCa RCS. Yes, that's the right example. So let's suppose that we have this I-shaped cross-section with post-tangent tendons. We have some action stages. Action stages like permanent load effects. Here are the pre-stressing stress. This example is taken as a reference example. You can also find it on our website, and due to verification or manual verification, we did not calculate the losses or creep. We needed to keep it simple. So it is very simple or easy example how to verify it also manually. So in action stages, we need to input permanent effects and pre-stressing effects, and in internal forces, we add other components like variable components of the loads. So in this case, we have some variable load. Normal force is 2000 kilonewtons, and bending moments. If I click on the results, I got immediately the code checks, and first capacity NMM, which is the method of interaction diagram or ultimate limit strain, is depicted. So what we see here, we see the interaction diagram and the acting internal forces intersection, so normal force and bending moment. If these internal forces are inside of this interaction diagram, then the cross-section satisfies this check and it's okay. If it's outside of this diagram, then we need to change something. In this case, we see that the utilization of the cross-section is 100%. It's exactly on the border of the stress strain diagram. It is useful to turn off this vestigial resistance, because here you can see the primary normal force caused by the decompression stress in prestressing steel. So this is the assumption which we need to do in order to get zero stress at the concrete, and in order to use classical reinforced concrete check. So here you can check the values, and these normal force corresponds to second order effects of the prestressing. So if we have a statically indeterminate structure, we have some secondary effects due to prestressing, and by external loads. So if we have some normal force caused by some load, then it is included here. And of course, this section can be also assessed by the response. So I will click on it and show you how the strain and stresses looks like. If it is prestressed section, we can click on these initials and increment of the stresses and strains and see what is happening. That at the beginning we have some initial state which includes permanent loads, primary effects of prestressing and creep and shrinkage. Then in the this increment we have the rest of the forces, this non-transmitted forces and strains due to variable permanent load effects. And if we sum it up, we got the resultant stress or strain distribution. So in this case, we can see that we are on the plastic branch of the concrete. In this case, there was used bilinear stress strain diagram, and the same is for prestressing steel, also on the plastic branch. Let me show you in materials in the navigator where we can check the materials. I think for this example we used this C40 stress strain diagram or concrete grade, and here we can switch between these two types of diagrams. So we have bilinear, and then we have prestressing steel, and also we can choose between inclined and horizontal top branch. Okay, so I hope that the assessing of resistance of a prestressed section is quite clear, and let's go on. So the third question or topic is focusing on elasticity of modulus of elasticity of concrete. So as you know, if it is prestressed, if you have a construction stages, you need to consider the changing of the material characteristics when having a concrete. So we distinguish between ULS and SLS states, and we have two types of modulus of elasticity. Everything is based on the Eurocode, so I think that you probably know these formulas. In these formulas, we take into account cement class, age of concrete, and also the modulus of elasticity is influenced by the type of aggregate. So when we have ULS assessment, we deal with FCD, which is designed concrete strength in compression. It is calculated by this formula, and if we assess the section at some particular time, we need to consider the real concrete strength. So if it's lower than 28 days, it is definitely lower than this FCD, which you know as a, for example, if we had 30 megapascal, it's 30 divided by gamma C. And the resultant modulus of elasticity is calculated by this formula, where we specific concrete strength is divided by this strain epsilon C2 or C3. It depends on the type of stress strain diagrams, which is the strain reaching the yield point. On the other hand, SLS states are based on this formula, and this modulus of elasticity is the second modulus. In IDEA StatiCa, you can choose if you want to calculate with this first one, second, or if you want to calculate with the tangent modulus, which is slightly higher. So we are again, I'm gonna show you the demo where you can find these values. So imagine that we have a pre-stressed saddle beam with some construction stages. I can show you that we have several stages, and we need to assess the this beam in each stage. So I go to Concrete Design 1D, go to Detailed Results. This means that I'm launching IDEA StatiCa RCS. And in action stages, where we were before, we have information about the stresses, effects of pre-stressing and things like that. And if we stretch this table, we can see initial state of the cross-section. And this initial state is defined by these characteristics. And in the last column, there are values for elastic modulus. So you can see that for ultimate limit state, we have these values. And after reaching 28 days, we have the same value. So it means that we do not consider higher values than FCD. And so, in other words, we do not take into account that the strength is getting higher and higher during the time. But in SLS states for for characteristic frequent or quasi-permanent combinations, we calculate with the values according to the formula in the code as it was depicted like a minute ago, and you can see that the values are rising. So theoretically, I can get infinite value in modulus of elasticity. And the values are the same for these SLS combinations. In the settings, if I click on code and select general chapter, you can check this G16 line modulus type, and here you can specify whether you want to calculate with secant or tangent modulus. Okay, I will close this and going back to the presentation. And we are approaching the fourth topic, and this is about the interaction. We got a lot of questions from our customers, how it is calculated and why there is 1000% of utilization, or usually they got 1000% of unsatisfying check. So it means that there is something wrong. So let me explain this. This interaction check is based on the response of the cross-section. That's why I explained this response at the beginning. It is always calculated, the response, even if it is not turned on in the control of results, because we use some parameters or results from response to shear and torsion check, and then also to interaction check. So the initial state of the interaction check is the response. If I have a section where we can find normal force, bending moment, and shear force, I need to do the interaction, or I should do. So first I need to calculate the contribution due to shear in longitudinal reinforcement. This formula, delta FTD, is based on strut and thigh methodology. So you have the shear force acting in the section, some angle of strut, and you calculate delta FTD, and then if we have this force, we can assess the strain due to shear or due to additional force in longitudinal reinforcement. We suppose that this additional strain is constant and is equally distributed on all longitudinal bars, and also pre-stressing steel. So once we have the strain, we can add it to this stress strain diagram and check if we are inside of this diagram. If yes, then we can find the corresponding stress, and once we have this stress, we can calculate the capacity, the remaining capacity in each reinforcing bar. So that this is done by this formula. And if there is a torsion, we can calculate the additional stress due to torsion. Again, there is the formula for that. That's how we get the additional stress. And then we can compare the capacity with the additional stress due to torsion. If we are within this capacity, we can easily find the corresponding strain here. If we are out of the capacity, then we usually get this unsatisfying check and this 1000% occur in this particular interaction check. So let me switch to RCS. So I have this composite section of type concrete to concrete with some reinforcement, shear reinforcement, and also post-tangent pre-stressing steel or tendons. I will go back to sections, and I can see that I have this, for example, this section, this extreme, and I can see 1000. And in this small table, I can see that the problem is in the interaction 1000. So I go to results, go immediately to interaction, and I can see some response. Again, we can switch between the type of display. So if we click on a diagram and, for example, look for the most tangent rebar, we can see where we are in the position, where we are, if we are on the plastic branch, or in this case inclined branch, how far we are from the limits, for example. And we can see that this 1000 is here. So there is not sufficient capacity for transmit the stress due to torsion. See, you can notice that there is no strain. There is this sign. So we weren't able to find the corresponding stress strain. So what we have to do, so if I switch to torsion, this is how we check the torsion in this section. We create this equivalent thin wall section. And why am I saying this? If we talk about torsion check, we need to focus the longitudinal or interaction check. We need to focus the longitudinal rebars inside of this thin walled section. So because this increment due to torsion is transmitted only by these rebars. So it doesn't matter if I have some reinforcement here or here outside of this thin walled section. It doesn't matter for the torsion. So I will go to reinforcement and try to increase the number of the rebars. For example, let's have 13 bars, and maybe let's have higher diameter of this reinforcement, which is effective for the torsion. Also, I recommend to use only one stirrup effective for the torsion, because then the equivalent thin wall section is created correctly. And we go to interaction, and okay, we still do not satisfy the interaction, but we have maybe different problem, and it is in shear reinforcement. So let's go back to reinforcement, and maybe I will click on this stirrup, and let's have higher diameter results, interaction, and see we have 80% of utilization and everything is okay. And if we click on the most tangent rebar, we can see that we are within the limits of the stress strain diagram and the problem is solved, and we do not have 1000% unsatisfying check anymore. Okay, and now we are getting to the last topic, and this is about importing of slabs or 2D elements from other softwares to IDEA StatiCa. So it is possible for these three kinds of software: CI Engineer, Axis VM, and Midas, in general both Gen and Civil. The procedure is a bit different for each of the software. I decided to show you a demo of SIA project and Midas, and Axis, we can only comment it. So I will start with the Axis. So if we have a, maybe I can show you some document. So if we have a type of shell, we can import the shell and deal with the 2D results, or we can define the rib and import the integrated plate forces to IDEA StatiCa. So either plate rib or 2D elements are possible to import, and then you can code check this section in IDEA StatiCa BIM. If we talk about the engineer, there are two possible ways how to check 2D element or plate element. The first one is again via plate rib, and the second one is to use integration strip. So it means that we cannot import directly these 2D elements or the results from 2D elements, but we need to modify them in CI Engineer. And third case is importing 2D results from Midas. So here we can import only 2D elements, and I will show you in a minute how to do it. So I'm gonna switch to Midas Civil. We have this simple plate of a certain thickness. It is loaded, and I've already calculated and have the results. So once we have the results, we can do the export to IDEA file. I'm going to click on export, and then I launch IDEA StatiCa, choose BIM, and import from other program. I need to find the right file, so it is Midas. Open it. Now I'm going to import the geometry and all results. So we need to wait. And we have this plate. And in the navigator, we have members 2D forces. And we have the imported results from Midas. What we see here. So first, we see some combination value. So it could be changed here in this pan. You can check out the results for the combination, or for example, due to one load case, G1, for example. I'm click to redraw, close this, and I have the different results corresponding to load case. I can check out the moments, mx, my, forces, shear forces, etc. And I can choose between viewing nodal results or results in centroids of the finite elements. This is just the viewer. I cannot change anything. The forces are directly imported from MIDAS. So the values correspond to the local coordinate systems defined in MIDAS. If I click on Design Members and click on this pen, that's how I'm going to create a section on the plate, and then I will send these sections to RCS. So I got this window. Again, I can switch between the values and see where are the extreme values. And I can also switch to different internal forces. And when we click to this button, I can rename it as I want. It can have the same reinforcement, or I can define several types of reinforcement. And I can, of course, change the position of the section where I want to check it. So if I click on this pin and click, for example, here, I'm going to create a section at this position. Then I'm going to create another section, for example, for the center of the plate. Click on it and I have created P2. Then I can create another one, for example, somewhere here. Click. I have many options how to define the position where I want to check it. So it's either by clicking, or I can define the particular number of the node or the element. The numbers are the same as in MIDAS Civil. So if you are oriented in these numbers, you can work with them. If we click OK, we generated the sections, and now we can go to Concrete Design 2D. I click on Result Classes. Those combinations are going to be checked. I have created 3 types of combination in MIDAS Civil, and I click on this Current Group button. By this, I generate the section from the plate, and in a second, I get this RCS application. Here are the sections I've created, and the software automatically recognize the type of the member. So it's a shell slab. It is determined by the internal forces, which were automatically imported or loaded from IDEA StatiCa or IDEA StatiCa BIM. So here we can see the values of plate forces, moments, and forces. And these values correspond to the centroidal values of the finite elements. That's how you can simply check it if the import was okay. So after selecting the current section, we can design the reinforcement. So this is done by this template. So we can say that we have 20 millimeters diameter, I don't know, 150. The same will be in the different direction. Remember that this is the plate, so we deal with the moments in both directions. and both edges, so upper and bottom fibers of the plate. And of course, we can define the links in this section. So this is a section of 1 meter wide and 350 high dimensions. This is taken from the thickness defined in Midas Civil. And after that, I can click on results and I can see what is the capacity and other checks of this section. I can also switch between the directions and see how it works for each direction. So I'm going to close this and go to SIA Engineer. So I've prepared some plate. So this is, now we are together, we will import integration strip from SIA to IDEA StatiCa. We have this plate, it is loaded, already calculated, and I have created this integration strip. This integration strip integrate the plate forces and create the internal forces as it was a beam member. How to generate the XML file from SIA Engineer? It is very simple. We go to, once it is calculated, we go to Tools, XML document, click on these 3 dots. I'm going to create a new document, load the template developed by IDEA StatiCa. So this one. Click OK. I have the XML file and I will do one modification. I will go to Load Cases, Internal Forces, and instead of importing all values, I'm going to specify what I would like to import. So I choose List, these 3 dots, and I have 3 bar elements or 3 beams or columns available, and this CM1 is the integration strip. So I'm going to select it, and then I can click on Export. That's this one. Okay, I will rename it. Export. I can close this and go to IDEA StatiCa. In this case, I need to have prepared a beam which corresponds to the integration strip. So it means that we have a cross-section of thickness equal to the height is equal to the thickness of the plate, and this dimension is supposed to be the same as the integration strip. Then we need to have the same geometry. So we switch to SIA. Here we have this. I'm going to hide it. Integration strip, which is 12 meter long. So that's correct, and you need to add the boundary condition, of course, so some supports. Then we go to user-defined forces and import the internal forces, integrated internal forces from the XML file which I have created. So this is this one plate, XML. I click OK, and here I have the information what is inside of this file. So it's the integration strip, length 12 meters, and there are some combinations and load cases. Right now, I'm importing only the load cases, but it is possible also to import the combinations, but it needs to be set up in SIA Engineer into document. I click OK, and in a while, I get the distribution of internal forces along the height of this beam or integration strip, and these forces must be equal to the forces in SIA Engineer. That's how you can easily check it. And we have these two load cases, LC1, LC2, and all internal forces are imported. So moments and shear forces, if they are in the section. I recommend to import other load cases apart from self-weight. It is better to calculate the self-weight here in IDEA StatiCa. So according to this checkbox, and these two load cases were imported, and we can of course change their settings. So for example, LC1 could be the permanent and LC2 could be the variable exclusive one. We can check in the variable load groups what are the characteristics or what are the combination factors for this LG2, so they can be also modified. Once you have this these settings right, then you have the combinations the same, and you can calculate it and assess this beam. And then, since we are running out of the time, I'm going to show you very briefly how we can deal with the plate ribs from SIA Engineer. So in this case, we can generate the XML file in SIA Engineer as it was shown before, and you imported it into Beam by this procedure. So where it is, so you will choose the right file, imported it into IDEA StatiCa Beam, and you have the whole structure here. And if there is a plate rib defined in SIA Engineer, we automatically find this member and create the corresponding cross-section. So we have a part of the plate and the actual rib. So, and you can have different characteristics, and it is always directed by the SIA engineer. So if you have, for example, effective with 1 meter, then it will be 1 meter. If there is specified the thickness, then the thickness must be the same. So that's how it is generate, and then it is sorry, I'm going to switch to the rib. Then it is a 1D member again, and we can assess this as a concrete 1D design. You can see that we can load the geometry of the plate, but the results are not available. So we need to work with integration strips or this plate ribs. Okay, so I believe that this is all from my side. Yes, okay, so I'm not sure if we have time for your questions. So maybe we skip this part and we will answer them via email, and I will pass the floor to Lukáš. Okay.
Okay, Betty, super great. Thank you for your inspiring webinar. So I will take a presenter, and I hope that Petya brought to you the deep insight to the problems of the interaction, capacity, and so on. Please wait a minute. I will tell you what will come. The upcoming webinar will be focusing on the connection and the BIM link between IDEA StatiCa and ETAPS. And you can also watch the recorded webinar, the last recorded webinar on our web page for Concrete. It was a topic how to define supports of the reinforced concrete structures in our CSFM model. After webinar, please fill in the short survey, and also the recording of this webinar will be delivered via email to you till 3 days. And if you're really interested in about IDEA StatiCa and you don't have it, so you can reach out about on our webpage for the trial. And all the other informations are on our support center on the webpage ideastatica.com. So thank you for your attention, and we will be looking forward to you on the upcoming webinar. So calculate yesterday's estimates. Bye bye.
Thank you for joining in. Bye bye.